a telescope floating 1 million miles from Earth just detected something it was never supposed to find. On a world 120 light-years away, James Webb picked up a chemical that on Earth is only produced by living things. Scientists ran the numbers 3 times. The signal held, "Tonight, we're going there." A warm ocean world wrapped in a thick atmosphere. A star system with 7 planets, packed tighter than anything in our own neighborhood. And a chemical signature that may mean we were never alone. Like and subscribe if the universe still has the power to shake you. Prepare yourselves. We begin. For most of human history, looking at the sky meant counting lights. You pointed a tube at the dark, gathered photons, and mapped what was where. Powerful telescopes gave us sharper images. Bigger mirrors gave us farther reach. But every single one of them was asking the same basic question. What is out there? James Webb is asking something different. It is asking, what is out there made of? That shift sounds small. It is not. It is the difference between seeing a stranger across a crowded room and actually reading the words written on their shirt. Here is how it works. Every atom in the universe, when it absorbs or releases energy, does so at a precise wavelength of light, not a range, a specific fingerprint. Carbon dioxide produces one. Methane produces another. Water vapor produces its own. These fingerprints never change. They are the same whether the molecule is sitting in a lab in California or floating in an atmosphere 120 light-years away. Webb was designed to catch those fingerprints. Its primary mirror stretches 18 feet across, made of 18 gold-coated hexagonal segments working as one surface. Gold, specifically, because gold reflects infrared light more efficiently than silver or aluminum, and infrared is exactly where molecular fingerprints live. The human eye cannot see infrared. Webb sees almost nothing else. When light from a distant star passes through a planet's atmosphere on its way to Webb, every molecule in that atmosphere leaves a mark on the light. Webb captures that marked light, pulls it apart by wavelength, and hands scientists a chemical inventory of a world they will never physically touch. The process is called transmission spectroscopy, and before Webb, our version of it was like trying to read a library through a keyhole. Webb kicked the door open. The telescope sits at a point in space called Lagrange Point 2, roughly 1 million miles from Earth, in the direction away from the star our planet orbits. At this location, the gravitational pull of Earth and that star balance out in a way that keeps Webb in a stable position relative to our planet. It also means Webb can keep its sunshield, a 5-layer barrier the size of a tennis court, permanently facing toward the inner solar system, keeping the telescope cold enough to detect heat signals from planets billions of miles away. Cold matters enormously. Infrared telescopes are essentially heat detectors. If the telescope itself were warm, its own heat would drown out the faint signals from distant worlds. Webb operates at -440 degrees Fahrenheit. At that temperature, even molecules in the telescope itself barely move. The result is a machine so sensitive it could theoretically detect the heat signature of a bumblebee at the distance of the moon. Think about what that means when you point it at a planet. Webb launched on December 25th, 2021, after more than 2 decades of delays, cost overruns, and engineering crises that nearly cancelled it entirely. Some scientists spent their entire careers building toward a telescope they were not certain would ever fly. It flew. It worked. And within its first 2 years of operation, it began returning data that nobody was fully prepared for. One piece of that data, from a planet called K2-18b, stopped the scientific community cold. What Webb found there is where this story really starts. K2-18b was not considered a priority target. When astronomers first catalogued it back in 2015, it was filed under interesting but uncertain. A planet about 2.5 times the size of Earth, orbiting a red dwarf star in the constellation Leo. It sat in what scientists call the habitable zone, the band of orbital distance where liquid water could theoretically exist on a surface. But habitable zone is a loose term. Planets in that zone have turned out to be hellscapes. The files stayed open. Nobody rushed. Then Webb started pointing at it. The first round of Webb observations on K2-18b, published in 2023, confirmed carbon dioxide and methane in its atmosphere simultaneously. That was already striking, because those two gases together in specific ratios suggest active biological or geological processes. But scientists held back. Methane can come from volcanism, carbon dioxide from basic atmospheric chemistry. Nothing confirmed yet. Then came the second, deeper round of analysis. Buried inside the spectroscopic data, the team at Cambridge University found a signal at a very specific wavelength, a signal that matched one molecule almost perfectly. That molecule was dimethyl sulfide. The team lead, Dr. Niku Madhusudhan, did not immediately celebrate. He ran the data again. His colleagues ran it again independently. They tested alternative explanations, other molecules with similar fingerprints, instrumental artifacts, statistical noise. Each time, the signal held. It was faint, sitting at roughly 2 sigma confidence, meaning it was not yet at the gold standard of certainty in physics, but it was there, persistently, stubbornly there. Here is why that matters. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. Microscopic ocean organisms release it as a metabolic byproduct. It floats up through the atmosphere, plays a role in cloud formation over the oceans, and gets detected in trace amounts across Earth's entire atmosphere. Scientists have searched for it in environments without life, in volcanic gases, in purely chemical reactions, in lab simulations of early planetary atmospheres. They have not found it forming in significant quantities without biological help. Finding it on a world 120 light-years away, in an atmosphere that also contains the carbon and hydrogen chemistry consistent with a warm ocean surface, was not supposed to happen yet. The field of astrobiology had worked for decades on the assumption that a biosignature detection was still a generation away, something for the next telescope after Webb, or the one after that. Webb found a candidate in year 2. The Cambridge team was careful in their language when they published. They called it a tentative detection. They were explicit that it requires confirmation. More observations are scheduled. The signal needs to reach 5 sigma before the scientific community will use the word confirmed. But even the tentative version sent a shock through the field that hasn't settled. Because here is the thing about K2-18b that makes this signal so difficult to dismiss. The planet is not just in the habitable zone. Its size, mass, and atmospheric chemistry all point towards something scientists have only recently started modeling seriously. A planet covered entirely in warm, liquid ocean, wrapped in a thick, hydrogen-rich atmosphere, with no rocky continents and no ice caps. A world that looks, chemically, like the best possible environment for marine microbial life in the observable universe. And something on it may be breathing. To understand why a single molecule is threatening to rewrite the history of life in the universe, you need to understand what that molecule actually does on Earth. Every summer, if you stand on a coastline near a productive stretch of ocean, you might notice a faint smell, something between the sea and cut grass, clean and slightly sharp. That smell is partly dimethyl sulfide drifting up from the water's surface. Below that surface, trillions of microscopic algae and phytoplankton are going about their lives, absorbing sunlight, cycling nutrients, and releasing this molecule as a biological exhaust. Dimethyl sulfide, sometimes abbreviated in scientific literature but more precisely called a sulfur-containing organic compound, forms when certain marine organisms break down a compound called dimethyl sulfoniopropanate, which they produce internally as a kind of cellular protection against osmotic pressure. When those organisms die, or get eaten, or stressed by temperature changes, the breakdown process accelerates, and dimethyl sulfide gets released into the water, then into the air. Earth produces roughly 50 to 60 million tons of it per year, nearly all of it from ocean biology. On a purely chemical level, you can make it in a lab. You can combine certain sulfur compounds with methane under the right conditions and get a trace of it. But here is the critical detail that scientists keep coming back to. In the scale and concentration needed to show up in a planetary atmosphere, the abiotic, meaning non-biological, production routes simply do not generate enough of it. The numbers don't work without a continuous biological source refreshing the supply. Life is not just a possible explanation for significant atmospheric dimethyl sulfide. On every model scientists have built, it is the only explanation that scales. This is why the detection on K2-18b hit so hard. It wasn't that scientists found a molecule that could suggest life. They found the specific molecule that, at planetary scale, essentially requires it. Now, there are serious caveats. The detection is still at low statistical confidence. The exact concentration is uncertain, and K2-18b's atmosphere may contain chemistry that hasn't been fully mapped yet, meaning there could be an exotic abiotic pathway no one has modeled for that specific type of world. Scientists are not rushing to plaster life confirmed on the front of every journal, but they are also not dismissing it, and that is the part worth sitting with. In the history of astrobiology, the field that studies the potential for life beyond Earth, scientists have frequently asked, what would a biosignature actually look like from a distance? What chemical flag would a living planet wave at a telescope 120 light-years away? Dimethyl sulfide was on that list. It was considered one of the cleaner candidates, precisely because it is hard to produce without life and hard to sustain without a constant biological source. Webb didn't just detect random chemistry. It may have detected exactly the molecule the field spent decades hoping to see. And that creates a problem nobody quite knows how to handle yet. Because if dimethyl sulfide is confirmed at K2-18b, the implications don't stop at one planet. They cascade outward across the entire framework of how rare life is supposed to be. Before we get there, though, there's a question nobody is talking about loudly enough. The scientists who found this signal didn't just run the data once. They ran it again, and each time, something unexpected kept holding. Science does not trust excitement. That is not a flaw. It is the design. When the Cambridge team first extracted the dimethyl sulfide signal from K2-18b's spectroscopic data, the lead researcher's first instinct was not to call a press conference. It was to assume something was wrong, a contaminated dataset, a miscalibrated detector, an atmospheric molecule with a similar fingerprint that got misidentified. In science, the boring explanation wins until it can't anymore. So they started looking for the boring explanation. The first check was instrumental. Webb has performed extraordinarily well since launch, but no instrument is perfect. The team examined whether the signal could be explained by detector noise, by calibration errors in the pipeline that processes raw Webb data, or by any known artifact in the telescope's performance history. They compared the signal against Webb's known quirks and blind spots. It didn't match any of them. The signal was not coming from the instrument. It was coming from the planet. The second check was chemical. Webb's spectrograph separates light by wavelength across a broad range simultaneously. That means when you detect a signal, you have to rule out other molecules that absorb light at nearby wavelengths. Dimethyl sulfide has a specific absorption feature, but there are other compounds that overlap partially with it. The team modeled dozens of alternative chemical combinations, testing whether any realistic mixture of known atmospheric gases could produce the same pattern without requiring dimethyl sulfide to be present. None of them replicated the signal cleanly. The fit was consistently better with dimethyl sulfide included than without it. The third check was statistical. 2 sigma confidence, which is where the signal currently sits, means there is roughly a 1 in 20 chance the detection is a random fluctuation in the data. That sounds manageable until you realize that in fields like particle physics, scientists require 5 sigma before calling something real, because at the scale of those experiments, 1 in 20 is not good enough. Astrophysics uses similar standards for major claims. 2 sigma is a flag, not a finish line. But here is what makes this particular 2 sigma signal different from most. The team didn't find it by hunting for dimethyl sulfide specifically. They ran a broad atmospheric retrieval, essentially asking Webb's data what molecules best explained the full spectrum. Dimethyl sulfide emerged from that analysis without being the thing they were looking for. Signals that show up unexpectedly, rather than being searched for directly, carry a different kind of credibility, because the confirmation bias that can inflate a targeted search doesn't apply. The team published their findings with full transparency about the uncertainty. They listed every caveat. They explicitly invited the scientific community to challenge their interpretation. In the months since, several independent groups have reanalyzed the same data. Some have been more skeptical. None have produced a clean alternative explanation that fully removes dimethyl sulfide from the picture. Additional Webb observations of K2-18b are scheduled. Each new transit of the planet in front of its star gives scientists another window to collect more photons, stack more data, and push the confidence level higher or lower. If the signal grows with additional data, it approaches confirmation. If it fades, it was noise. Either way, the scientific machinery is now committed to finding out. What nobody fully prepared for is what happens if the answer is yes. Because the world where this signal is being detected is not a rock in space. It is something far stranger and far more alive-seeming in every way except the one thing not yet confirmed. For most of the history of exoplanet science, astronomers sorted planets into rough, familiar categories. Rocky worlds like Earth and Mars, gas giants like Jupiter, ice giants like Neptune. These categories came from our own solar system, and for a while, they felt complete enough. Then Webb started looking closely at worlds between 1 and 4 times Earth's size, and scientists realized they had been missing an entire category of planet that may be the most common habitable environment in the galaxy. They started calling them Hycean worlds. The name combines hydrogen and ocean, which describes exactly what these planets appear to be. Worlds with vast liquid water oceans beneath thick hydrogen-rich atmospheres. No solid continents, no ice poles. Just warm, deep ocean stretching from horizon to horizon under skies made of hydrogen, helium, and trace gases, with pressures and temperatures kept stable by the sheer mass of atmosphere above. K2-18b fits this profile almost perfectly on current models. It is about 8.5 times the mass of Earth and about 2.5 times the size. Its density, calculated from how much it pulls gravitationally on its star during transits, is too low for a purely rocky composition and too high for a pure gas envelope. The numbers point toward a large liquid interior beneath a thick atmosphere. Current best estimates suggest K2-18b may have an ocean hundreds of miles deep. Hundreds of miles. Earth's deepest point, the Mariana Trench in the Pacific, drops just under 7 miles below the surface. The pressure there is more than 1,000 times what humans experience at sea level. Almost nothing survives at those depths, except extremophile organisms that have evolved to handle conditions most life would find instantly lethal. Now imagine an ocean with a floor that may never be reachable. An ocean that goes so deep the water at the bottom may not even behave like normal water anymore, but instead transition into exotic high-pressure ice phases while still being warm enough that the layers above remain liquid. An ocean where the entire concept of a seafloor might not apply. Hycean worlds were largely ignored in the search for life for a simple reason. They looked inhospitable to anything resembling the life we know. The hydrogen atmosphere lets through radiation that would sterilize a surface. The The pressures would crush any organism that drifted too deep. There's no land, no rocky substrate, no tidal pools to concentrate chemistry. But in 2021, Madhusudan's team at Cambridge published a paper that reframed the question entirely. They argued that the upper layers of a Haitian ocean, the zone between the crushing deep and the hostile atmosphere, could be warm, chemically rich, and shielded enough to support microbial life. Not just support it, potentially allow it to thrive on a scale that dwarfs anything possible on a rocky world like Earth. The surface area of a global ocean, uninterrupted by any landmass, is vastly larger than the ocean's surface on Earth. More surface means more chemistry. More chemistry means more opportunity for life to take hold and maintain itself. The paper didn't claim life exists on these worlds. It claimed that scientists had been crossing off entire categories of planet without thinking carefully enough about what life actually needs. Life needs liquid water, a chemical energy source, and time. Haitian worlds may have all three in extraordinary abundance, which means the universe may be far more crowded than the old models suggested. And what lives in that ocean, if anything does, would look nothing like what you're picturing. If K218b is the most intriguing single candidate, TRAPPIST-1 is the most intriguing system. 40 light-years from Earth, in the constellation Aquarius, there is a red dwarf star about the size of Jupiter. It is dim, cool by stellar standards, and has been burning steadily for an estimated 7.5 billion years, nearly 2 billion years longer than the star at the center of our own solar system has existed. Around this quiet, ancient star orbit, 7 confirmed planets, all of them roughly Earth-sized. All of them in orbits so tight that the entire system would fit inside the orbital path of Mercury. 3 of those 7 sit inside the habitable zone. 3 Earth-sized rocky worlds orbiting the same star, all at the right distance for liquid water. The probability of finding one such planet in a random stellar system is already low enough to make headlines. 3. Around one star, at the same time, is the kind of number that makes theorists revise their models overnight. TRAPPIST-1 was first discovered in 1999, but its full planetary system wasn't confirmed until 2017, when a coordinated global observation campaign tracked multiple transits simultaneously. The announcement triggered one of the largest single-day traffic spikes in the history of NASA's website. Webb has since pointed at this system repeatedly. The results so far have been sobering in some ways and tantalizing in others. The innermost of the 3 habitable zone planets, designated the first of the 3 inward ones, appears to have lost its atmosphere or never developed a thick one. Webb detected no clear atmospheric signal, which likely means stellar radiation stripped it down to bare rock. That was the bad news. The 2nd and 3rd habitable zone planets have not yet been ruled out. Webb's observations are ongoing, and the atmospheric signals, if they exist, are at the edge of detectability. Each transit gives scientists a few more data points. The picture is not complete. What makes TRAPPIST-1 so compelling despite these challenges is sheer redundancy. One planet losing its atmosphere doesn't disqualify the system. With 7 planets in tight formation, the chemistry, the debris fields, the volcanic outgassing, the potential for material to transfer between worlds during impacts, all of this creates an interconnected environment that might actually increase the chances of life taking hold somewhere in the mix. There is another layer to this system that doesn't get discussed enough. Because the star is so small and the planet's orbit so close, the gravitational dynamics are extreme. These planets interact with each other constantly, pulling on each other's orbits in patterns that keep the whole system rhythmically stable. Tidal heating from those gravitational interactions could warm the interiors of planets even if starlight alone isn't enough. It's the same process that keeps Jupiter's moon Europa liquid beneath miles of surface ice. TRAPPIST-1 could be doing the same thing to rocky planets. Not just one, potentially several. And here is the detail that changes the entire calculation. If microbial life ever took hold on any one of these 7 worlds, impacts could theoretically carry rock fragments, carrying organisms to the neighboring planet. The distances between worlds in this system are small enough that survival during transit is not impossible. Life, once started, might not stay on one planet. But before we get to that possibility, there is something more fundamental to understand. How exactly does Webb see the chemistry of a world 40 light-years away without ever touching it? The answer is stranger and more elegant than most people realize. The planet doesn't send Webb a message. Webb intercepts one that was never meant for it. When K2-18b passes in front of its host star from Webb's perspective, something subtle happens to the starlight. Most of it travels straight through empty space and hits Webb's mirror directly. But a tiny fraction of it passes through the thin shell of atmosphere surrounding the planet's edge. That fraction is not the same when it arrives. The molecules in that atmosphere have absorbed specific wavelengths out of the light. Each molecule has taken exactly the wavelengths it recognizes and left everything else untouched. What reaches Webb is starlight with specific colors missing, and those missing colors are a map. Webb's instrument suite includes spectrographs, tools that spread incoming light across a range of wavelengths, the way a prism spreads white light into a rainbow, but far more precisely, and extending far into the infrared where human eyes are blind. The resulting spectrum is a bar graph of absorption. Deep dips at certain positions, shallower dips at others, flat regions where no molecule interfered. The scientists take that bar graph and compare it to a library. Every known molecule has been measured in labs on Earth and catalogued with its precise absorption fingerprint. You overlay known patterns onto the observed spectrum and ask what combination of molecules best explains every dip and flat region simultaneously. When you find a combination that fits, you have identified what the atmosphere is made of. This is transmission spectroscopy, and it sounds straightforward until you appreciate the numbers involved. The fraction of starlight that passes through K2-18b's atmosphere during a transit is roughly 1 in 10,000. The signal scientists are extracting from that fraction, the trace of dimethyl sulfide, is a fraction of that fraction. Webb is detecting a molecular fingerprint in a whisper of light that has traveled 120 light-years and carries the information of an entire alien atmosphere in a variation so small it would have been invisible to every light telescope built before it. The feat is comparable to detecting the scent of a single candle burning in a city from an airplane at night by analyzing nothing but the light the candle adds to the city's glow. Each transit observation lasts only a few hours, the time it takes the planet to cross the face of its star. During that window, Webb stares without blinking. Every photon matters. Scientists stack observations from multiple transits to build statistical confidence, each pass adding a thin layer of signal over the noise until patterns emerge. Webb is not designed to do this forever. It carries a limited supply of the propellant used to maintain its precise orientation in space. Current estimates give it roughly 20 years of operational life, which sounds long but is extraordinarily tight when you consider how many targets exist and how many transits each one requires for meaningful data. Scientists are making choices right now about which planets get precious observation time and which ones wait. K2-18b has received a significant share of that time already. TRAPPIST. One's planets are in the queue. Every scheduling decision is a prioritization of which worlds humanity investigates first. But Webb's technique is not the only tool in the search. Inside the data it has already returned from K2-18b, there is a chemical contradiction that scientists keep circling back to, one that should not be possible without something actively maintaining it. In chemistry, certain molecules are enemies. Carbon dioxide and methane, sitting in the same atmosphere, in the ratios Webb detected on K2-18b, should not last long. Methane is reactive. Given enough time, it breaks down under stellar radiation, reacts with other atmospheric chemicals, and gets converted. In a planet-sized atmosphere with no replenishment source, methane disappears over geological timescales. If you find significant methane in an atmosphere, the clock is running. To keep that clock from running out, something has to keep adding methane back. On Earth, the primary sources of methane are biological. Microbes called methanogens produce it as a metabolic byproduct. Wetlands release it. The digestive systems of animals release it. Decaying organic matter releases it. Earth's methane budget is almost entirely biological or biologically driven. Remove life from Earth's atmosphere, and within a few million years, the methane concentration drops sharply. Carbon dioxide, meanwhile, stays elevated. The ratio between them shifts dramatically. What Webb measured at K2-18b is a carbon dioxide and methane ratio that sits closer to the biologically active end of what models predict for a living ocean world than to what you'd expect from purely chemical processes. Alone. This is not a smoking gun. Scientists are careful to say that. Geological sources of methane exist. Certain types of volcanic and hydrothermal activity can produce significant methane. A world with the right interior chemistry could potentially generate methane abiotically and sustain it for some period without life's involvement. The debate around this is active and unresolved, but here is the layer that makes this atmospheric chemistry more compelling than the methane alone. The ratio between carbon dioxide and methane is just one piece. Webb also detected the relative absence of carbon monoxide, a molecule that tends to accumulate in hydrogen-rich atmospheres undergoing purely chemical reactions. On Earth, organisms consume carbon monoxide as part of metabolic cycles, keeping its atmospheric concentration low. The same depletion pattern that biology creates on Earth appears to be reflected in K2-18b's atmospheric chemistry. This is called a chemical disequilibrium signature. No single molecule is the tell. The whole pattern is the tell. When multiple atmospheric gases sit in ratios that chemistry alone trends away from, something is pushing back against chemistry. On every world where scientists have studied this pattern carefully, the thing pushing back has been life. The concept was proposed decades ago as a remote detection method for life. Carl Sagan's team used it in 1993 to test whether a probe flying past Earth would be able to detect life here. They analyzed the chemical disequilibrium in Earth's own atmosphere and found it obvious. Oxygen and methane together should not coexist at Earth's levels. They do, because life maintains both. K2-18b's disequilibrium is not as pronounced as Earth's. The signal is subtler, but the direction of the deviation matches what life, specifically marine microbial life, would be expected to produce on an ocean world with a hydrogen-rich atmosphere. 3 independent chemical signals pointing the same direction: elevated methane, depleted carbon monoxide, and now the dimethyl sulfide candidate. Each one individually explainable without biology. All 3 together, on the same world, in a configuration that fits a living ocean planet. That is not something scientists expected to be debating this early in Webb's mission. The next thing Webb confirmed on this same world is something even harder to explain away. Of all the molecules Webb has detected in exoplanet atmospheres, water vapor is the one that changes everything when it shows up in the right place. Not because water is rare. The universe is saturated with hydrogen and oxygen, the 2 elements that form water. It exists in comets, asteroids, interstellar clouds, and the atmospheres of gas giants. Detecting water vapor in a planetary atmosphere is not, by itself, astonishing. What is astonishing is where K2-18b sits when that water vapor shows up. It is inside the habitable zone. It has surface pressure conditions compatible with liquid water. It has a temperature range in the right ballpark. And it has water vapor in its atmosphere, meaning there is active exchange between whatever liquid reservoir exists on or near the surface and the atmosphere above. That exchange is the part that matters. On Earth, the water cycle is continuous. Liquid water evaporates, rises into the atmosphere as vapor, condenses into clouds, falls as rain, and returns to the surface. This cycle is not just a weather pattern. It is a chemical conveyor belt that moves nutrients, distributes energy, and creates the constantly renewed surface conditions that biology depends on. The presence of water vapor in an atmosphere is evidence that this kind of cycle is active. Webb confirmed water vapor in K2-18b's atmosphere in the 2023 dataset, alongside the carbon dioxide and methane. It is one of the more robust detections, higher statistical confidence than the dimethyl sulfide signal, consistent across multiple analysis approaches. What it implies about what is underneath those clouds is not confirmed, but it is directionally clear. The most natural explanation for water vapor circulating in an atmosphere over a planet with K2-18b's mass and temperature is that there is liquid water below, actively evaporating and cycling. An ocean. A specific model published by Madhusudhan's group before Webb even launched predicted this pattern. They described what a warm, hydrogen-rich Hycean world with an active ocean surface would look like spectrally. They listed the molecules you would expect to detect and in roughly what ratios. When Webb's data came back, the match to that model was striking enough that the team described it as validation of the Hycean hypothesis. Now, alternative explanations exist. Some researchers have proposed that K2-18b might be a mini Neptune, a world with a thick gas envelope over a high-pressure icy interior, with no liquid water ocean at all. On that model, the water vapor could come from chemical reactions in the upper atmosphere rather than from evaporation off a surface. The debate between these two interpretations, Hycean ocean world versus waterless ice interior planet, is one of the most active arguments in exoplanet science right now. Here is what makes the Hycean interpretation harder to dismiss: the temperature. Webb's detection of multiple infrared wavelengths allows estimates of the atmospheric temperature profile at different altitudes. Those estimates, combined with the planet's distance from its star and the chemistry of its atmosphere, point towards surface or near-surface temperatures that fall comfortably within the range liquid water can exist in. The ice interior model requires more exotic conditions that fit the data less cleanly. The simplest explanation, an ocean world with active evaporation and a chemically complex atmosphere, keeps winning on model comparisons. That world is waiting there, 120 light-years away, covered in water, wrapped in chemistry, generating signals that biology would explain more neatly than anything else. But the word comfortable should not enter your mind, because nothing about what actually lives on that world, if anything does, would survive a single hour in the conditions that exist there. The word habitable is one of the most misleading terms in modern science communication. When astronomers say a planet is in the habitable zone, they mean one specific thing. At that distance from its star, given a range of possible atmospheres, liquid water could theoretically exist on or near the surface. That is the entire definition. It says nothing about radiation levels, gravity, atmospheric toxicity, tidal forces, storm intensity, or any of the other factors that determine whether an organism can actually survive there. K2-18b's habitable status is not a reassurance. It is a baseline minimum. The gravity on K2-18b is estimated at roughly 2.5 times Earth's. Every single biological process that involves structure and movement on Earth, bones, blood circulation, fluid distribution, cellular architecture, evolved under one specific gravity over billions of years. Placing any Earth organism on K2-18b's surface would be like pressing it into an invisible vice. For a human, the weight alone would be immediately incapacitating. Most multicellular organisms from Earth would be crushed or physiologically compromised within hours. But surface gravity is almost a minor concern compared to the atmospheric situation. K2-18b's atmosphere is hydrogen-rich, which is a fundamentally different chemical environment from Earth's nitrogen-oxygen mix. Hydrogen is the lightest element, and in sufficient concentrations, it creates a flammable, chemically reactive envelope around the planet. Complex biochemical reactions, the kind that maintain cell function in everything from bacteria to blue whales, were engineered by evolution for an oxygen-available environment. In a hydrogen-dominated atmosphere, that biochemistry does not simply slow down. It stops working entirely or produces entirely different reaction chains. The atmospheric pressure is another factor. Webb's data constrains K2-18b's surface pressure to somewhere between tens and hundreds of times Earth's sea level pressure. That range has enormous consequences for what life can physically do at the surface interface. At those pressures, gases dissolve into water differently, chemical reactions proceed along different pathways, and the density of the medium through which any organism must move is dramatically higher. And then there is the radiation environment, which is where things get genuinely hostile. K2-18b orbits a red dwarf star. Red dwarfs are cooler than stars like the one our planet circles, which is why they appear red rather than white or yellow. But cool does not mean calm. Red dwarfs are magnetically active, prone to sudden violent eruptions called stellar flares that blast out far more ultraviolet and X-ray radiation in minutes than the star emits in months of steady output. K2-18b, sitting in the habitable zone of a red dwarf, is significantly closer to its star than Earth is to its own. The radiation environment is intense. Any life on K2-18b would not be life adapted to a gentle, Earth-like environment. It would be life that evolved under conditions Earth biology would find apocalyptic, and that evolved a completely different set of solutions to the problems of staying alive. That life, if it exists, would be strange beyond our current biological imagination, not slightly different, fundamentally unlike anything in any textbook. And yet, life on Earth includes organisms that thrive inside nuclear reactors, survive in pure acid, and reproduce at temperatures that would cook a human alive. Life has a way of finding corners we didn't think to look in. The TRAPPIST, one system has its own version of this problem, and on those worlds, it is even more extreme, because their star doesn't just flare occasionally, it never really stops. Every planet in our solar system rotates. Earth turns once every 24 hours, Mars every 24 and a half. Even Venus, which rotates backward and impossibly slowly, still rotates. Rotation gives a planet a day-night cycle. It distributes heat. It prevents any single region from baking forever or freezing permanently. Most of the habitable zone planets Webb is now studying do not rotate freely. When a planet orbits close enough to its star, the star's gravity stretches the planet slightly along the line, connecting them, creating a bulge. Over time, as the planet rotates, that bulge gets tugged backward, slowing the rotation. This continues until the planet's rotation period matches its orbital period exactly. The planet then always shows the same face to its star, just as Earth's moon always shows the same face to Earth. This is called tidal locking. Every single planet in the TRAPPIST, one system is almost certainly tidally locked. The same is plausible for K2-18b. Think about what this means for the surface. One hemisphere receives continuous stellar radiation. No sunsets, no nighttime cooling, just a permanent day with light and heat beating down on exactly the same ground forever. The other hemisphere faces permanent darkness. No warming, no light, just cold expanding outward towards space. Between them, a narrow band where the star sits on the horizon, neither rising nor setting. A region sometimes called the terminator zone or the twilight belt. The temperature difference between the day side and the night side of a tidally locked planet is extreme. For rocky worlds close to active stars, dayside temperatures can reach hundreds of degrees, while the night side sits near absolute zero. Nothing about that sounds like a place life could exist. But scientists looking carefully at this problem have started asking a different question. What if the interesting zone is not the dayside or the night side? The Terminator Belt, that narrow ring of perpetual twilight, experiences moderate temperatures where the dayside heat bleeds into the transition zone. Atmospheric circulation on tidally locked planets tends to drive permanent storm systems around this belt as hot air from the dayside rises and cold air from the night side flows in to replace it. These circulation patterns create potentially stable atmospheric conditions along the Terminator that might not exist on either extreme hemisphere. Some models suggest that the Terminator regions of tidally locked rocky worlds could maintain liquid water. Some include stable habitats where biology could potentially function. The biology would need to handle the unusual lighting, the constant stellar horizon position, the strange seasonal patterns caused by the planet's slightly elliptical orbit instead of its rotation. But none of those challenges are categorically unsurvivable. On ocean worlds, like K2-18b, the situation is different again. Water is an extraordinary heat distributor. Deep ocean currents move enormous amounts of thermal energy around the planet. If K2-18b has a global ocean kilometers deep, that ocean could act as a planetary thermostat, absorbing energy on the day side and releasing it on the night side, moderating the temperature extremes to ranges that matter for biology. The same process happens on Earth. Oceans prevent extreme temperature swings between day and night, between pole and equator. On a full ocean world, that effect would be global and constant. This is one reason Hycean worlds keep coming out as surprisingly strong candidates in habitability models despite their alien conditions. But even with the best ocean thermostat working in its favor, any life on K2-18b still has to survive what its star sends at it. And its star has something to say about that. Red dwarf stars are the most common type of star in the galaxy. Roughly 70% of all stars are red dwarfs. They burn cool, they burn slow, and they burn for an extraordinarily long time. A red dwarf like TRAPPIST, one is expected to live for roughly 10 trillion years. For comparison, the universe itself is only about 13.5 billion years old. These stars will still be burning when everything else in the sky has gone dark. That sounds great for life. Long-lived, stable energy source, plenty of time for evolution to do its work. The problem is magnetic. Stars generate magnetic fields through the movement of electrically charged plasma in their interiors. The Sun has a magnetic cycle roughly 11 years long, during which its field grows, distorts, and eventually flips polarity, releasing energy through solar flares and coronal mass ejections along the way. These events are energetic enough to occasionally disrupt satellites and power grids on Earth. But Earth has two layers of protection, a strong magnetic field and a thick atmosphere that absorbs the bulk of the radiation before it reaches the surface. Red dwarfs are smaller and cooler, but their magnetic activity is disproportionately intense compared to their size. They flare more frequently and, relative to their normal output, more powerfully. TRAPPIST. One has been observed releasing flares that, in terms of the energy they deliver to nearby planets, are dramatically stronger than anything typical for larger, hotter stars. During a major flare event, the ultraviolet radiation reaching the surfaces of the inner TRAPPIST, one planet spikes to levels many times higher than the steady baseline. K2-18b's star, a red dwarf called K2-18, shows similar behavior. Flare events have been detected in its observational record. The question of whether K2-18b has a magnetic field strong enough to deflect charged particles during these events remains open. Smaller, ocean-covered worlds may or may not generate magnetic fields the way Earth's iron-nickel core does. For life on the surface, or near surface of any of these worlds, a stellar flare is not a problem to manage around. It is a recurring extinction-level radiation event. Ultraviolet radiation at those intensities breaks apart DNA. It destroys the chemical bonds that hold complex molecules together. It oxidizes organic compounds faster than biological repair mechanisms can compensate. A single major flare could sterilize any exposed surface within hours. This is why many researchers who take the possibility of life on these worlds seriously focus almost entirely on subsurface or deep ocean scenarios. Kilometers of water are an extraordinarily effective radiation shield. The ocean depths on Earth receive essentially zero ultraviolet radiation regardless of what is happening on the surface. If K2-18b has an ocean hundreds of miles deep, every organism living below the upper tens of yards is effectively shielded from stellar flares by a barrier of liquid water no space weather can penetrate. Webb cannot yet see beneath an ocean's surface. Its spectroscopic tool reads atmospheric chemistry, not what exists below the atmospheric interface. The chemical signals that suggest life, the dimethyl sulfide, the methane, the disequilibrium pattern, would have to originate from organisms near enough to the surface to allow their metabolic products to escape into the atmosphere, which means if life is producing those signals, it is surviving in the most exposed layer of its world, in a radiation environment that should make that almost impossible unless it has found a way. And life's history on Earth is a long story of finding ways. Life on Earth began in an environment that would be considered catastrophically hostile by today's standards. About 4 billion years ago, Earth had no ozone layer. Its star blasted the surface with ultraviolet radiation at levels that would have destroyed most modern organisms instantly. The atmosphere was rich in carbon dioxide, methane, hydrogen sulfide, and ammonia, with almost no free oxygen. Temperatures fluctuated wildly. The surface was being struck regularly by asteroids large enough to vaporize entire ocean basins. If you showed that environment to a modern biologist and asked whether life could start there, the honest answer would be, probably not, by today's standards. And yet life did start there, within a few 100 million years of Earth's formation, in conditions that would have destroyed any organism that evolved later. This is what scientists call the survivability problem, but in reverse. Life didn't wait for Earth to become comfortable. It emerged in discomfort and made itself comfortable enough to keep going. Every adaptation that modern organisms use to survive radiation, chemical extremes, and pressure came from lineages that evolved specifically because they needed it. The same logic applies to any world where life might be emerging. The biology wouldn't look like Earth life trying to survive in a bad environment. It would look like organisms that never knew any other environment, built from the ground up to thrive in exactly those conditions. On K2-18b, researchers have identified several mechanisms that could protect life from the intense radiation environment of its red dwarf star. The first and most obvious is depth. An organism living more than 30 feet below a water surface receives almost no ultraviolet radiation regardless of what is happening above. At 300 feet, it is essentially zero. At 3,000 feet, the radiation environment is completely dominated by the natural radioactive decay of minerals rather than anything coming from the star above. The second mechanism is biological. On Earth, microorganisms that live in high radiation environments have evolved extraordinary DNA repair capabilities. Some bacteria, like Deinococcus radiodurans, can survive radiation doses that would kill a human at roughly 3,000 times over. They accomplish this through redundant, highly efficient molecular repair systems that continuously fix radiation-induced DNA damage faster than it accumulates. Organisms on K2-18b would have billions of years to evolve similar or more sophisticated versions of this capability. The third mechanism is chemical. Certain organic pigments, including some produced by microorganisms on Earth, absorb ultraviolet radiation and convert it into harmless heat. Mats of microorganisms using such pigments create biological sunscreen layers that protect the organisms beneath them. On a world where UV pressure is a constant, the evolutionary pressure to develop these pigments would be enormous. The organisms that survived would be the ones that either dove deep or built their own shields. There is a fourth possibility that researchers are beginning to take seriously. If K2-18b has a magnetic field, even a weak one, it would deflect the charged particle streams that accompany stellar flares, the most damaging radiation type for complex chemistry. Even a field far weaker than Earth's could be enough to channel the worst of the particle radiation toward the poles, leaving the equatorial ocean regions relatively shielded. Life is not passive. It does not sit exposed and wait to be destroyed. It adapts, evolves, and modifies its local environment in ways that increase its own survival odds. 4 billion years of that process on Earth produced organisms that can live in boiling acid, vacuum, and solid rock. 4 billion years on, K2-18b could produce something we have no framework to even describe yet. And that gap in our framework is exactly where the scientific community started fracturing. Science is supposed to be a unified pursuit of truth. In practice, when the data touches something as consequential as extraterrestrial life, it becomes a contact sport. The detection of dimethyl sulfide, methane, carbon dioxide disequilibrium, and water vapor on K2-18b has not produced consensus in the scientific community. It has produced a very public, very pointed disagreement that is still actively unfolding. On one side are researchers, primarily the Cambridge group led by Madhusudan, who argue that the cumulative weight of the atmospheric chemistry signals points toward a world where biology is the most parsimonious explanation. They are not claiming life is confirmed. They are claiming that among all the hypotheses that fit the data, a biologically active ocean world fits better than anything else currently on the table. On the other side are researchers who argue that the statistical confidence of the key signals, particularly dimethyl sulfide, is too low to draw any meaningful conclusion. That alternative abiotic pathways for the observed chemistry have not been fully explored, and that the Heysian world model itself remains a theoretical construct that has never been validated against a confirmed real-world example. Both sides are correct about something. The dimethyl sulfide signal is genuinely at the edge of detectability. 2 sigma is not enough to build a scientific consensus on. Every researcher involved in the debate agrees on that point. The disagreement is about what to do with a suggestive but uncertain signal, how much weight to give it, and how urgently to pursue it. The deeper disagreement is epistemological. It is about what counts as evidence. Some researchers argue that biosignature science has a false positive problem. There are documented cases where atmospheric signals initially proposed as biosignatures turned out to have abiotic explanations. In 2022, a widely publicized detection of phosphine on Venus, a gas associated with biological processes on Earth, was later challenged by researchers who identified possible abiotic production mechanisms on Venusian terms. The excitement around that detection and the subsequent controversy left scars. The community became more cautious about early biosignature claims. Others argue that excessive caution is its own form of scientific error. If life is out there and all available signals are deliberately weighted towards skepticism, the risk is not confirming a false positive. It is missing a true positive, missing the actual detection of life because the bar was set so high that a real signal couldn't clear it. The stakes are not symmetrical. Falsely claiming life exists somewhere it doesn't is embarrassing and requires a correction. Failing to recognize life when it actually announces itself is a different kind of failure entirely. This tension is not new in science. It is the same argument that played out during every major paradigm shift in history, when the evidence for a new idea built up slowly, ambiguously. and in ways that existing frameworks were reluctant to accommodate. The people who waited for 5 sigma evidence before taking the idea seriously often waited too long. The people who jumped at 2 sigma sometimes sent the field chasing ghosts. For K2-18b, the resolution will come from more data, more Webb observations, more transits, more photons collected until the signal either solidifies or dissolves. The next observation window for K2-18b is not far away. Scientists on both sides of the argument are waiting. But what they are actually waiting to confirm or rule out is more complicated than it sounds, because even oxygen, the most famous potential biosignature of all, turns out to be a liar. For most of the history of astrobiology, oxygen was the holy grail. The logic seemed bulletproof. Oxygen is highly reactive. In a planetary atmosphere, it constantly combines with rocks, metals, hydrogen, and organic molecules, getting locked away in compounds. An atmosphere rich in free oxygen should deplete itself over geological time. The only known mechanism that can keep pumping oxygen back into an atmosphere fast enough to maintain significant concentrations is photosynthesis. Organisms using light to split water molecules and releasing oxygen as a byproduct. Therefore, oxygen equals life. Detect it on another planet, announce the discovery, schedule the press conference. The problem is that this reasoning held up under the conditions scientists had in mind when they developed it. Conditions like Earth's, where the star is relatively stable, the planet is rocky, and the starting atmospheric chemistry is roughly familiar. When researchers started building detailed models for different types of planets orbiting different types of stars, the oxygen story started fraying. Several mechanisms can produce significant free oxygen without biology. The most prominent is photolysis. Ultraviolet radiation from a star can break apart water molecules in a planet's upper atmosphere, releasing hydrogen and oxygen. Hydrogen is light and can escape the atmosphere into space, especially from lower gravity worlds. Oxygen is heavier and sticks around. Given enough time, enough ultraviolet radiation, and enough water in the upper atmosphere, a planet could accumulate an oxygen-rich atmosphere through purely abiotic chemistry. Simulations showed this process could be particularly efficient around red dwarf stars during their young, highly active phases when they emit intense ultraviolet for hundreds of millions of years before settling into more stable behavior. A planet sitting in the habitable zone during that early violent period could potentially accumulate what looks like a biologically significant oxygen atmosphere through nothing more than prolonged radiation exposure. Another mechanism involves high-pressure photochemical reactions in hydrogen-rich atmospheres. Under the right conditions, these reactions produce oxygen as an intermediate product that can build up before reacting away. The chemistry is complex and not fully mapped for every possible planetary scenario, but the principle is established. A third pathway involves carbon dioxide photolysis. Stars that emit the right ultraviolet wavelengths can break carbon dioxide into carbon monoxide and oxygen. If the conditions for the recombination reaction are unfavorable, oxygen builds up. What this means for the search for life is uncomfortable but important. A telescope detecting oxygen in an exoplanet's atmosphere cannot automatically conclude that life is present. The detection is necessary but not sufficient. Context matters enormously. The type of star matters. The planet's atmospheric composition beyond just oxygen matters. The presence or absence of other gases that should accompany a biotic oxygen source matters. This is exactly why the biosignature conversation shifted in recent years toward chemical disequilibrium signatures and molecules like dimethyl sulfide that are harder to produce abiotically at scale. Scientists learned that the obvious biosignature, the one that seemed definitive, was actually a false friend. The search became more subtle, and that subtlety is exactly why the K2-18b detection is structured the way it is, built on multiple lines of overlapping chemical evidence rather than a single molecule. The team was deliberately trying to avoid the oxygen trap. Dimethyl sulfide was chosen as a candidate biosignature precisely because it lacks the abiotic escape routes that oxygen has. It is a harder molecule to explain away, which is why what happens next in this story is stranger and more unsettling than any single detection. The history of biosignature research is, in part, a history of nature finding loopholes. Every time scientists proposed a molecule as a reliable indicator of life, careful analysis eventually revealed a scenario where chemistry alone could produce it without any organism involved. Methane, volcanic outgassing, oxygen, photolysis of water, phosphine, deep planetary pressure and chemistry. Each candidate had a story that ended with an abiotic escape route. Dimethyl sulfide has been examined through this same lens, and the results are different. To understand why, you need to know what it takes to produce dimethyl sulfide on a planetary scale. The molecule requires a specific organic chemistry chain, sulfur compounds, carbon compounds, and specific catalytic conditions that bring them together in a sequence that produces dimethyl sulfoniopropanate first, then breaks it down into dimethyl sulfide as a secondary product. On Earth, this entire chain runs inside living cells. The organism does not intend to make dimethyl sulfide. It is a metabolic exhaust product from cellular processes that evolved for entirely different reasons. The abiotic version of this chemistry exists in principle. In a lab, with controlled conditions, trace amounts of dimethyl sulfide can be produced from certain sulfur-methane reactions. No serious scientist denies this. The question has never been whether it is possible to make dimethyl sulfide without life. The question is whether you can make enough of it, consistently enough, to maintain detectable atmospheric concentrations on a planetary scale. The models say no. In every simulation run for Hycean world atmospheres, the abiotic production of dimethyl sulfide falls orders of magnitude below the concentrations that would register in a transmission spectrum from 120 light-years away. The chemistry simply does not run fast enough without a biological engine driving it. The molecule is reactive, meaning it degrades relatively quickly in a planetary atmosphere. Without a continuous replenishment source, atmospheric concentrations drop toward undetectable within thousands of years. For dimethyl sulfide to appear in Webb's data, something has to be making it constantly, at scale, across enough of the planet to keep the atmospheric concentration high enough to leave a fingerprint in light that has traveled more than 1,000 trillion miles. That is not a lab result, that is a planetary process. The implications of this distinction are what makes the scientific community uncomfortable in a way that the oxygen debate never quite managed. Oxygen had its abiotic out, which allowed researchers to stay cautious indefinitely. Dimethyl sulfide's abiotic out requires such extreme conditions, producing such small quantities, that claiming it as the explanation for a planetary scale atmospheric signal requires inventing new chemistry that has not been observed anywhere. That does not mean it is impossible. The universe contains environments humans have never modeled, with chemistry humans have never run. K2-18b might be doing something chemically unique that produces dimethyl sulfide at scale without biology. The possibility cannot be ruled out. But the probability hierarchy is shifting. And in science, probability hierarchies matter. When the simplest explanation, the one that requires the fewest unverified assumptions, is that life is producing dimethyl sulfide on a warm ocean world, and every attempt to construct a non-living alternative requires piling exotic condition upon exotic condition, the scientific principle that favors simpler explanations starts pointing in one direction. That direction has not been confirmed, but it has not been closed off either. And when you start asking what the organisms producing this signal might actually look like, the answer stops being a chemistry question and becomes something else entirely. Stop picturing little green creatures. If life exists on K2-18b, and current evidence suggests the question is at least worth asking seriously, It would bear essentially no resemblance to anything in any science fiction film. It would not resemble complex animals. It would probably not even resemble the more advanced single-celled organisms on Earth. What it would most likely look like is something closer to the oldest, most fundamental life forms Earth ever produced, adapted beyond recognition to conditions no Earth organism has ever experienced. The closest analog researchers reach for is the deep ocean hydrothermal vent communities found on Earth's ocean floor. In the 1970s, oceanographers sent a submersible down to explore hydrothermal vents along mid-ocean ridges and found something nobody expected: an entire thriving ecosystem in a place with zero sunlight, crushing pressure, and water temperatures ranging from near freezing to over 700 degrees Fahrenheit within a few yards. This ecosystem runs entirely on chemosynthesis, the metabolic process of deriving energy from chemical reactions rather than light. It does not depend on the star. It does not need the surface. It is a completely self-contained biosphere, fueled by the chemistry of the planet's interior. Those vent communities are not the exception on Earth. In terms of total biomass and the sheer number of species, they represent one of the most productive and diverse environments on the planet. Life did not grudgingly adapt to survive there. Life thrives there. On K2-18b, researchers envision something analogous but vastly larger. An ocean world with no solid seafloor, or a seafloor so deep that it exists under exotic high-pressure ice phases, would still generate hydrothermal chemistry wherever water contacts geologically active material. The heat driving those reactions comes from gravitational compression and the decay of radioactive elements in the planet's interior. Neither source requires the star. Neither source is diminished by a stellar flare. Neither source requires a surface. The organisms living in such an environment would be microbial, tiny, single-celled life forms, capable of the metabolic efficiency needed in a chemically extreme environment. They would likely process sulfur compounds as part of their energy cycle, which is exactly the type of chemistry that produces dimethyl sulfide as a byproduct. They would probably form dense mats or colonies, the way microbial biofilms form on Earth's vent structures, creating communities rather than isolated individuals. Their cell membranes would be built from entirely different molecular scaffolding than Earth life, because the pressure, temperature, and chemical environment of K2-18b's ocean would make Earth-style lipid bilayers unstable. Life on a hydrogen-rich world might use entirely different structural molecules, possibly ether-linked lipids rather than ester-linked ones, possibly something with no Earth analog at all. Their genetic machinery, if they have any, might encode information using the same fundamental principle as Earth life, that specific molecular sequences carry heritable information while using completely different molecular letters, or it might use an information storage mechanism that has no counterpart in any organism ever studied on Earth. This is not speculation for its own sake. Every one of these design variations has been observed somewhere in Earth's biodiversity, in organisms that evolved to handle chemical extremes. Life is not committed to one blueprint. It experiments constantly, and on K2-18b, 4 billion years of experimentation under completely alien constraints would produce results that are genuinely alien. The dimethyl sulfide in K2-18b's atmosphere, if confirmed, would be exhaust from that machinery, the exhaust of an entire planetary ocean's worth of microbial life going about its strange alien business, completely unaware of the gold-coated telescope 120 light-years away that just noticed the smell. What comes next is the question that no scientific paper has fully prepared anyone for, because if this is microbial life, the simplest possible version of biology, what does that mean for what else might be out there? There is a gap in the history of life on Earth that does not get enough attention. Life appeared on this planet roughly 3.5 to 4 billion years ago. For the first 2 billion years of that history, essentially nothing happened in terms of complexity. Microbes ruled. Single-celled organisms colonized every available environment, evolved extraordinary chemical diversity and transformed the planet's atmosphere and geology. But they stayed small. They stayed simple. The jump to multicellular complexity did not happen until roughly 600 million years ago, after 2 billion years of microbial dominance. 2 billion years of nothing but microbes. That gap is not an accident. The transition from single-celled to multicellular life required a specific set of evolutionary innovations, so improbable that many biologists consider it one of the most remarkable events in the history of life on Earth. It required cells that could cooperate rather than compete. It required the development of cellular specialization, meaning different cells doing different jobs within one organism. It required new mechanisms for intercellular communication, for programmed cell death, for coordinated development. Some researchers believe this transition may have happened only once in Earth's history, not once per lineage, once total. From that single event descended every plant, every animal, every fungus that has ever lived. If that interpretation is correct, and it is seriously debated in evolutionary biology, then complex life may be extraordinarily rare, even on planets where microbial life is abundant. What Webb's data on K2-18b points toward, based on the chemical signatures and the modeling of Hycean world environments, is the microbial end of this spectrum. Dimethyl sulfide is a metabolic exhaust product. The organisms that produce it on Earth are phytoplankton and bacteria. They are among the most ancient, most successful, and least complex life forms on this planet. The detection of dimethyl sulfide does not suggest kelp forests and fish. It suggests something older, smaller, and more fundamental than that. This distinction matters enormously for the broader question of life in the universe. If microbial life is confirmed on K2-18b, it would establish that the chemistry of life is not unique to Earth. It would show that at least one other planet independently developed, or possibly inherited, the biological machinery to produce complex organic molecules at scale. That is a profound result, but it would not tell us that intelligence is common. It would not tell us that complex organisms are likely. It would tell us that the first step, the one that takes chemistry and converts it into something that metabolizes, reproduces, and evolves, is possible in at least 2 places in the galaxy. Whether the second step, the one that takes microbial life and transforms it over billions of years into something that builds telescopes, is equally possible or uniquely difficult, would remain entirely open. This question splits the scientific community in a different way than the biosignature debate does. Everyone agrees that confirming microbial life elsewhere would be revolutionary. The disagreement is about what it would imply for complex life, for intelligence, for civilizations. Some researchers believe microbial life is common throughout the galaxy, and that given enough time and the right conditions, complexity follows naturally. Others believe the gap between microbial and complex life is a nearly impassable barrier, and that Earth's complex biosphere is a cosmic accident unlikely to be replicated anywhere else within observable distances. Both interpretations accept the same basic premise, that microbial life, if it exists on K2-18b, is almost certainly not looking back. But then a different question emerges, one that shifts the entire frame of the conversation. What if we have been searching for the wrong type of signal entirely? For 60 years, the dominant strategy in the search for extraterrestrial life has been radio silence. Not actual silence, the opposite. Astronomers have pointed enormous radio telescopes at the sky, searching for structured electromagnetic signals, patterns that could not be explained by natural processes, the kind of organized transmission that a technological civilization might send. The assumption behind this strategy was reasonable. If intelligence exists out there, it would probably use electromagnetic communication, just as humanity does. And some of that communication would leak into space, or be deliberately aimed at other star systems. This is the biosignature approach's technological cousin, where biosignatures look for chemical evidence of biology, technosignatures look for engineering evidence of intelligence, radio emissions, laser pulses, industrial pollution in a planetary atmosphere, megastructures large enough to alter a star's light curve, the accumulated waste heat of an industrial civilization, detectable as an infrared excess around a star that has no natural explanation. The radio search has been running since 1960. In 6 decades of listening, one anomalous signal has been recorded. In 1977, a radio telescope in Ohio detected a strong narrowband signal from the direction of the constellation Sagittarius. The astronomer who noticed it circled the printout and wrote the word "wow" next to it. That signal has never been detected again. Its origin remains unknown and is classified officially as unexplained. One anomaly in 60 years of listening. Some researchers argue this tells us something important. Technological civilizations either do not exist in detectable numbers, or they do not communicate in ways our instruments are designed to receive, or they communicate on timescales and at frequencies we have not yet explored. Others argue that 60 years is nothing on cosmic timescales, and that the volume of sky and the range of possible frequencies humanity has actually searched represents a tiny fraction of the total search space. In terms of the electromagnetic spectrum, humanity has thoroughly searched roughly the equivalent of a drinking glass's worth of water from an ocean, but the distinction between biosignatures and technosignatures raises a question with no clean answer. Which is more likely to be detectable first? A planet full of microbes producing trace chemicals, or a civilization advanced enough to build detectable technology? The answer might be neither. And it might be that the thing separating detectable microbial life from detectable technological life is exactly the gap discussed in the previous chapter, the one between microbes and complexity, and that gap may be where the entire story of intelligent life in the universe gets filtered down to almost nothing. That filtering concept has a name in astrophysics. It is called the Great Filter, and it becomes the most disturbing idea in this entire story once you understand what it means for where we are right now. But before we get there, the radio silence problem itself deserves its full weight, because the universe is 13.5 billion years old. If technological life emerged anywhere in the galaxy in the first half of that history, it would have had billions of years to expand, communicate, and reshape detectable portions of the cosmos. The sky is silent. That silence is a data point. It says something. Scientists are not yet agreed on what. The universe is approximately 93 billion light-years across in the observable portion alone. It contains an estimated 2 trillion galaxies. Our own galaxy holds somewhere between 200 and 400 billion stars. Roughly half of those stars are estimated to have at least one planet in the habitable zone. Work through those numbers. Even if life arises on only 1 in a million habitable zone planets, there should be hundreds of millions of living worlds in this galaxy alone. Even if only 1 in a billion of those develops technological intelligence, there should be hundreds of civilizations currently active in the Milky Way. This reasoning was formalized in the 1960s by a physicist named Enrico Fermi, who reportedly sat down to lunch one day, did a rough version of this calculation, and asked a question that has not been satisfactorily answered since: where is everybody? That question is known as the Fermi paradox, and it sits at the center of every discussion about life in the universe, like a stone nobody can move. 60 years of radio searches have returned silence. No structured signals, no beacon broadcasts aimed at promising star systems, no detectable engineering on the scale that a civilization with billions of years of technological development should be capable of. The galaxy does not look inhabited, it looks empty, and those two things cannot both be true simultaneously unless one of the numbers in the calculation is catastrophically wrong. The possibilities are not comfortable. One option is that the calculation is simply wrong, that life is far rarer than even the most pessimistic estimates, that the steps between chemistry and biology, between biology and complexity, between complexity and intelligence, and between intelligence and detectable technology are each so improbable that across the entire observable universe, the total number of civilizations that have ever existed might be countable on one hand. Maybe we are alone, not approximately alone, but genuinely, cosmically alone in a way that makes the universe's size feel less like abundance and more like an enormous amount of empty. Another option is that civilizations exist but are undetectable by our current methods. They use communication technologies we have not imagined. They operate on timescales that make our 60-year search statistically meaningless. They are present but quiet, choosing not to broadcast, or having evolved past the need for electromagnetic communication entirely. A third option is that civilizations arise and then disappear before they can make a lasting mark, that the average lifespan of a technological civilization measured against the timescale of the universe is brief. A few thousand years, a few hundred, long enough to build radio towers, not long enough to make a signal that reaches other star systems before some internal catastrophe ends the whole experiment. A fourth option is the one that nobody likes to think about, that something happens to intelligent life predictably and consistently at a certain stage of development, something that prevents any civilization from reaching the scale of cosmic detectability, something that is either behind us in evolutionary history, already survived, or ahead of us, waiting. That fourth option is what the Great Filter theory is really about. And the position of K2-18b's possible life within that framework changes the entire meaning of the discovery. Here is the uncomfortable collision. The Fermi paradox has always been an argument about probability. Nobody had actual data on how common life was beyond Earth. Scientists argued from theory, from estimates, from the logic of chemistry and evolutionary biology. The numbers were educated guesses built on educated guesses. The paradox was real, but it was abstract. You could hold the tension of life might be common and the sky is silent without one directly contradicting the other, because you had nothing concrete on either side. Webb just changed that. If the dimethyl sulfide signal on K2-18b is confirmed, it is no longer a theoretical exercise. It becomes an actual data point. Life appeared independently within 120 light-years of Earth. For cosmic distances, that is, next door, the nearest plausible galaxy is 2.5 million light-years away. TRAPPIST-1 is 40 light-years away. K2-18b is 120. In the scale of the observable universe, these are all essentially the same address. If life arose on K2-18b, the statistical implication is that life is not rare. It is not a once-per-galaxy miracle. It is something that happens with reasonable frequency in environments where the conditions are right. Chemistry finds a way, microbes get started, biology runs. And that is where the Fermi paradox does not get weaker in response to this evidence. It gets stronger. Because if microbial life is common, and if some fraction of that microbial life eventually develops complexity and intelligence, and if some fraction of that intelligence eventually develops technology, and if some fraction of that technology eventually becomes detectable from light years away, then the sky should not be silent. Given a galaxy this old, the accumulated output of multiple technological civilizations should be detectable somewhere. Not everywhere, but somewhere. The silence is not explained by life being rare if K2-18b's signal is real. The silence needs a different explanation. The two most discussed explanations within the scientific community lead in opposite directions, and the direction you find more plausible depends on one critical question: where is the Great Filter? Is it behind us, in the evolutionary history that separates lifeless chemistry from microbial life, from complex life, from intelligence? If the Great Filter already happened, and humanity is on the far side of the hardest step, then the silence makes sense. We pass through something almost no life passes through, We are the exception, the lucky ones, or is the great filter ahead of us? Is there something that every technological civilization reaches? A stage of development or a capability that consistently leads to self-destruction or forced silence? Something that looks, from the outside, like an abrupt end to the story? Something that our civilization is currently approaching without knowing the shape of what is coming? If life is confirmed on K2-18b, that confirmation makes the behind-us scenario less likely, because it moves the great filter past the biology step. Life, at least microbial life, is not the hard part. Something else is. And if we look at where humanity currently sits, at a moment of unprecedented technological capability, self-inflicted existential risks, and expanding ability to alter the conditions that sustain biological life on this planet, the ahead of us scenario starts demanding attention in a way that feels personal. The most unsettling reading of K2-18b's data is not that we might not be alone. It is that the fact we might not be alone is exactly the kind of result that makes the Fermi paradox more frightening, not less. The Great Filter was named and formalized by economist Robin Hanson in 1998. The concept is simple. Between the formation of stars with planets and the development of spacefaring civilizations, there must be at least one step that is so difficult, so improbable, that it filters out virtually all candidates. The observable absence of alien civilizations demands it. Something stops life from reaching cosmic detectability almost every time. The question is where in the sequence that filter sits. The evolutionary path from bare chemistry to detectable technological civilization involves roughly 8 major transitions, each building on the last. The synthesis of self-replicating molecules from raw chemistry, the development of the first living cells, the emergence of complex cells with internal compartments, the evolution of sexual reproduction, the transition to multicellular organisms, the development of animals with sophisticated sensory and nervous systems, the emergence of language using social intelligence, the development of industrial technology. Any one of these steps could be the great filter, the one step that almost never succeeds. If the filter is at the very beginning, the chemistry to life transition, then a confirmed detection of life on K2-18b would immediately rule it out as the filter. Life would have been demonstrated to arise readily in the right conditions. That would be good news for life in general, but it shifts the filter to a later step, possibly one that is much closer to where humanity currently is on the path. Here is the version of this logic that keeps some researchers awake at night. If simple microbial life is common, and current evidence is beginning to suggest it might be, and if complex multicellular life is also demonstrably possible given enough time and the right planetary conditions, then the great filter must lie somewhere in the later steps, the ones between complex life and civilization, or worse, the ones between early civilization and long-term survival. Every civilization that has ever existed on Earth has had a finite lifespan. The ones that ended did not always fail from external threats. Some collapsed from internal instabilities, resource depletion, political disintegration, failure to manage the consequences of their own technology. These collapses happened on timescales of hundreds to thousands of years, tiny fractions of a planetary lifespan. A technological civilization that lasts 2,000 years and then destroys itself would leave almost no trace after 1,000,000 years. No signals, no megastructures, no engineered environments. Just a quiet, formerly inhabited planet cycling slowly back toward chemical equilibrium. The Fermi paradox would look exactly the same whether civilizations never arose, or whether they arose constantly and consistently, eliminated themselves shortly after reaching detectable capability. This is the most uncomfortable version of the Great Filter argument, and it is the one that K2-18b's possible life makes increasingly hard to dismiss. If life is not the filter is in our future, and we are the test case. None of this is certain, None of it is even close to confirmed. But the logic is internally consistent, the silence is real, and the K2-18b data is pulling the conversation from abstract possibility towards something that requires actual positions. What is confirmed is what a detection like this would mean, not just for humanity's philosophical self-understanding, but for the actual material reality of life on Earth, starting with how we understand our own origin story. Scale matters. The observable universe is roughly 46 billion light-years in radius. Our galaxy is about 100,000 light-years across. The nearest star to our own is just over 4 light-years away. The confirmed exoplanet with the most compelling current biosignature evidence sits 120 light-years from Earth. In universal terms, 120 light-years is not a neighboring star system. It is the same hallway, same neighborhood, same zip code on any map that shows the full galaxy. A confirmed biosignature at that distance would not be evidence that life exists somewhere out there in the cosmic vastness. It would be evidence that life exists right here, densely, in the local region of the galaxy, which means throughout the galaxy, which means almost certainly throughout the universe. That inference cascades through every framework humanity has ever used to understand its own place in existence. The scientific implications are immediate and fundamental. If life arose on K2-18b independently, the biochemistry of life is not a peculiarity of Earth. It is a robust solution that chemistry finds whenever the right conditions exist. The specific molecules of life, the amino acids, the nucleotides, the metabolic cycles, or at least their functional analogues, are written into the physics of the universe rather than being an accident of one particular planet's history. This changes the timeline of how life should be expected to arise on other worlds. It changes models of how chemistry transitions to biology. It changes estimates of how many worlds in the galaxy currently host life. The number goes from maybe some to almost certainly many. The origin of life on Earth itself gets reframed. For decades, researchers have debated whether life's building blocks arrived here from space or developed entirely through local chemistry. Confirmation of life on K2-18b would add serious weight to the idea that the chemistry of life is widespread in the galaxy, making delivery of biological precursors through comets and asteroids not just possible but expected. The implications for climate science and planetary habitability are also significant. Understanding what types of planets can sustain biology, and for how long, and under what conditions, directly informs how scientists model Earth's long-term future. K2-18b's Hycean environment represents a habitability regime that Earth's own history does not provide direct data on. Studying it teaches humanity something about the full range of conditions under which life can persist. Beyond science, there is the simpler, more personal weight of the discovery. Humanity has operated for its entire conscious history with one data point on the question of life in the universe. One planet, one biosphere, one example of chemistry becoming something that eventually builds telescopes and asks questions. A second data point does not just add to the picture, it changes the picture entirely. It transforms what was an extraordinary exception into what appears to be a pattern, and patterns carry implications that exceptions do not. The universe begins to look like a place where life is expected, not miraculous, where Earth is not a special case but a successful implementation of a widespread process, where the question is no longer whether life exists elsewhere, but how different it is, how complex it becomes, and how often it survives long enough to notice itself. One of the oldest and strangest proposed answers to that last question involves the possibility that life on Earth and life on K2-18b share more than parallel chemistry. They might share an ancestor. The idea that life travels between star systems sounds like a premise from a story someone invented. It is not. It is a scientifically serious hypothesis with a proper name, published models, and an active research community. The hypothesis is called panspermia, and its most ambitious version, lithopanspermia, proposes that life can survive transfer between star systems aboard rocky debris ejected by large impacts. The mechanism begins with an asteroid or comet striking a planet hard enough to eject surface material into space. This happens. Earth has received rock fragments from Mars. Scientists have identified Martian meteorites on Earth's surface, blasted loose by ancient impacts and captured by Earth's gravity after spending millions of years in transit. If Mars ever had life, and if any of those meteorites contained living organisms or viable biological molecules, life could have crossed from Mars to Earth or from Earth to Mars. The direction would depend on which planet hosted life first. Extending this logic to interstellar distances requires organisms to survive an extraordinarily harsh journey. Ejection velocity sufficient to escape a planetary system, millions to hundreds of millions of years of exposure to cosmic radiation in deep space, and then deceleration through entry into a new planetary atmosphere without being incinerated. The numbers make this implausible for most life, but not for all of it. Certain bacterial spores on Earth have been demonstrated to survive radiation doses far beyond what they would encounter in interstellar transit over 1 million years. Shielded by even a few feet of rock, the radiation exposure in deep space drops to levels that extremophile organisms could potentially survive indefinitely in a dormant state. The entry heating problem is real, but may be survivable in larger fragments where the interior remains cool during atmospheric entry. The distances involved are the serious obstacle. 120 light-years is not comparable to the distance between Earth and Mars. At the velocities achievable by ejected debris, crossing 120 light-years would take on the order of millions to tens of millions of years. Bacterial spores have not been tested at those timescales. However, the Milky Way has been rearranging itself gravitationally for billions of years. Star systems that are currently separated by 120 light-years may have been much closer to each other in the past. Stellar drift and galactic dynamics mean that the ancestral distance between K2-18b's system and our own could have been significantly smaller during the early periods when life was getting established on either world. Panspermia between K2-18b and Earth is not confirmed, not considered likely by most researchers, and faces serious unresolved physical challenges. But it is not ruled out either. And if the biochemistry of K2-18b's possible life turns out to bear structural similarities to Earth life, rather than being completely alien, it would push the panspermia hypothesis from interesting speculation towards something that demands a proper scientific answer. More fundamentally, the concept of panspermia reframes what a biosignature detection means. If life can travel between star systems, then a detection of life on K2-18b is not necessarily evidence that life arose independently twice. It might be evidence that life arose once, spread, and the galaxy we live in is seeded with versions of that original biology running their own evolutionary experiments across hundreds of worlds. A garden, not a desert, with seeds scattered from a single ancient source. Whether the garden is that densely seeded can now, for the first time in history, actually be calculated, because Webb has given scientists hard numbers where before there were only guesses. In 1961, astronomer Frank Drake stood at a whiteboard at a scientific conference in West Virginia and wrote out a series of variables in a simple multiplication chain. Each variable represented a factor in estimating the number of communicating civilizations currently active in the galaxy. The result was not meant to be a precise answer. It was meant to be a framework for organizing ignorance, a way to identify what humanity would need to learn in order to answer the most important question it had ever asked. That equation has 7 terms. Before Webb, the first 3 were reasonably well constrained, and the last 4 were essentially guesses with error bars the size of continents. Webb has begun moving 2 of those unknowns into at least partial territory. The first variable is the rate of star formation in the galaxy. well established at roughly a few new stars per year. The second is the fraction of those stars with planets. Webb and its predecessor observatory have now confirmed that planets are extremely common, with most stars hosting at least one, and rocky planets being nearly ubiquitous. These first two terms are now solid. The third term is the fraction of those planets that could support life. Before Webb, estimates ranged across many orders of magnitude. Webb's work on Hycean worlds and habitable zone atmospheres is beginning to constrain this term. The number of planets with atmospheres in the right temperature range, with water vapor, with chemical conditions plausibly compatible with biology, appears to be larger than pre-Webb estimates. Not dramatically, but meaningfully. K2-18b type worlds may be more common than the rocky habitable zone planets that dominated earlier models. The fourth term is the fraction of potentially habitable planets where life actually arises. This is the term that a confirmed K2-18b biosignature would most directly address. If life arose twice in the same galactic neighborhood within 120 light-years, the fraction is high, not every habitable world necessarily, but high enough to push the downstream numbers significantly. The fifth term is the fraction of life-bearing planets that develop intelligence. The sixth is the fraction of intelligent species that develop detectable technology. The seventh is the average lifespan of a communicating civilization. These three remain deeply uncertain, subject to everything the Great Filter argument implies. But Webb has done something the Drake equation never had before. It has begun generating real constraints on the biological terms from actual observation rather than theoretical modeling. The equation is no longer entirely abstract. Two of its most uncertain middle terms are starting to acquire observational anchors. Running the equation with even conservative estimates based on Webb's current data, the number of potentially active civilizations in the galaxy does not go to zero. It does not even go to small. The number that falls out, even with pessimistic values for the intelligence and technology terms, is large enough to make the Fermi paradox more acute, not less. The math says there should be others. The sky says otherwise. Something in between is wrong. And figuring out which part of the calculation fails is no longer purely an academic exercise. It is the most consequential question that a technological civilization in its early phase of development could possibly be investigating. But the conversation is not stopping at science, because the morning after a confirmed detection is announced, the questions stop being about chemistry and start being about what humanity is actually going to do about it. There is no international law governing the confirmed discovery of extraterrestrial life, not a partial framework, not a draft treaty under review, no law. The United Nations has protocols for asteroid deflection coordination, for the management of orbital debris, for radio frequency allocation in space communications. These exist because specific concrete scenarios were anticipated, and governments decided to create frameworks before the problems arrived. For the discovery of life beyond Earth, no government on this planet has formally created or ratified any binding policy framework that covers what happens next. This gap was identified by researchers in astrobiology, space law, and international relations well before Webb launched. In 2019, a group of researchers published a paper explicitly calling attention to the absence of post-detection protocols for biological discoveries and recommending that governments begin developing them. The paper received polite attention in academic circles and essentially no response from any government. The scenario that falls between existing legal cracks is K2-18b specifically. It is not contact. Nobody has received a message. Nobody has met anyone. There is a planetary atmosphere exhibiting chemical signals consistent with biological processes 120 light-years away, on a world no human or spacecraft will reach in any currently imaginable time frame. What rights, if any, does that world have? Under existing frameworks, the answer is none. International space law, primarily governed by the 1967 Outer Space Treaty, prohibits nations from claiming sovereignty over celestial bodies, but places no restrictions on what can be done to them. Since it was written at a time when the concept of doing anything to a distant exoplanet was science fiction, the treaty does not address planetary contamination beyond the solar system. It does not address the rights of potentially living worlds. It was written for a technological era where Mars was the frontier. The ethical questions compound quickly. If life is confirmed on K2-18b, does humanity have an obligation to protect it from any future technological interference? How would that obligation be enforced across different nations with different scientific priorities and different philosophical frameworks about the value of non-human life? Does the form of life matter? Microbial organisms on a distant ocean world do not inspire the same intuitive moral response as a whale or a chimpanzee, but the philosophical case for their protection is arguably stronger given their uniqueness. What about future missions? No spacecraft can reach K2-18b on any current technology within a human lifetime, but directed energy propulsion concepts and generation ship proposals are actively discussed in serious aerospace engineering circles. If humanity develops the capability to send probes or eventually crewed missions to K2-18b in some distant future, what protocol governs whether that is allowed, and who decides? More immediately, what does the announcement of a confirmed detection trigger geopolitically? Scientific discoveries do not stay in scientific journals. They become national narratives. They shift cultural identities. They have historically been used to justify ideological claims that the scientists involved never intended. The confirmation of life on K2-18b would not just be a scientific announcement. It would be a political event, a religious event, a philosophical event, and a legal event simultaneously, in a world that has prepared for none of those four. Governments are not ready, institutions are not ready, and the evidence that the announcement may be coming sooner than anyone expected is already in Webb's data. The question is not whether a confirmed biosignature detection would shake human civilization. It would. The question is in which directions and how permanently. Religious traditions have wrestled with the idea of extraterrestrial life for centuries, long before the scientific tools to address it existed. The results are more varied than the popular narrative suggests. Some theological frameworks treat the question as relatively minor, pointing to doctrines that place Earth's human story at the center of their cosmology, regardless of what exists elsewhere. Others incorporate the possibility of life elsewhere into a larger understanding of creation, where an abundant universe reflects the scope of a creative principle rather than contradicting it. Still, others treat confirmed extraterrestrial life as a theological crisis requiring significant reinterpretation of foundational texts. Vatican astronomers, notably, have publicly stated that the discovery of extraterrestrial life would not fundamentally threaten Catholic doctrine. Similar statements have come from theologians in several traditions. These represent genuine intellectual positions reached through careful reasoning, not denial. The more extreme reading, that extraterrestrial life disproves the existence of meaning or divine presence, is not the only religious response available, and probably not the most common one. The political dimension is less philosophically nuanced. Scientific discoveries of this magnitude do not arrive in a political vacuum. They arrive in news cycles, in election years, in periods of existing international tension. A confirmed detection of life on K2-18b would immediately be claimed, shaped, and weaponized by political actors in every country where it registered as significant. National space agencies would seek ownership of the discovery narrative. Governments with interests in space resource exploitation would use it to argue for the urgency of expanded space programs. Governments with interests in maintaining existing social orders would manage the announcement to minimize destabilizing effects. The first nations to publicly frame the discovery would shape the global narrative for years. How it is described in initial press conferences, whether it is framed as a triumph of one nation's scientific investment or as a shared human achievement, would have measurable effects on international scientific cooperation for a generation. Human identity, on the deepest level, rests on certain background assumptions so foundational that they are rarely examined. One of them is that the story of life, intelligence, and consciousness is primarily or uniquely a human story. That the universe is not actively indifferent to human existence, but is, at minimum, unoccupied by other storytellers. That when humanity looks at the cosmos, it is the only thing looking back. A confirmed detection does not replace humanity. It does not diminish a single human life or achievement. But it removes that assumption in a way that cannot be undone. The universe becomes, permanently and verifiably, a place where life is not an exception. The human story becomes one story among potentially many, and nothing in human civilization has ever operated from that premise before. What makes this psychologically complex is that the change is irreversible. You cannot undiscover life on another planet. The framework shifts, and every subsequent human endeavor occurs inside that new framework, whether the people involved consciously acknowledge it or not. Researchers who have thought carefully about this moment often point to a surprising finding about how humans actually respond when the news arrives, and the results of those studies do not match what most people predict for themselves. When researchers began systematically studying how people respond to information about extraterrestrial life, they expected to find significant anxiety, existential distress, and social disruption. The intuitive assumption was that a discovery of this magnitude would be destabilizing, particularly for individuals with strong religious beliefs, strong national identities, or psychological frameworks that center human uniqueness. The data did not cooperate with that assumption. A series of studies conducted over the past decade, several of them specifically designed to test responses to realistic simulated biosignature announcements, produced consistent results that surprised the researchers running them. The dominant psychological response to news of extraterrestrial life was not fear. It was not grief for lost specialness. It was curiosity, followed by awe, followed, in many participants, by a reported sense that the universe felt more alive than it had before, which most people described as a positive shift. Even among participants with strong religious beliefs, the response was less disruptive than predicted. Several studies found that religious individuals actually reported slightly higher positive affect in response to hypothetical extraterrestrial life news than non-religious individuals, possibly because many religious worldviews already contain frameworks for an inhabited, purposeful universe and find the confirmation of life elsewhere consistent with those frameworks rather than threatening to them. The distress responses that did appear tended to be specific. They correlated not with the fact of life's existence elsewhere, but with the perceived implications for humanity's relative standing. Participants who reported negative reactions were more likely to be responding to the idea that humanity might be less technologically advanced than whatever was out there, or that extraterrestrial life might present a competitive or existential threat. The mere existence of microbial life on an ocean world 120 light-years away, posing no conceivable physical threat, generated minimal anxiety even in participants who initially predicted it would disturb them. There is a notable gap between predicted and actual responses that psychologists call the impact bias. People consistently overestimate how much major events will change their emotional state and for how long. Applied to this scenario, it suggests that when confirmation arrives, the disruption to daily human life will be far more modest than the scale of the scientific event might imply. This does not mean the discovery is psychologically insignificant. It means the significance is different from what people imagine. The shift is quieter, deeper, and more durable than a short-term emotional crisis. It is a permanent update to the background context of human existence, integrated gradually rather than experienced as a sudden shock. The studies also found something worth noting about communication. How the announcement is framed matters enormously. Announcements that led with uncertainty, explained the evidence carefully, and avoided dramatic language about implications produced significantly better psychological integration than announcements framed in maximally dramatic terms. People could handle the information, they could not always handle the performance around it. This finding has influenced how scientific organizations are beginning to think about the announcement strategy. The question is no longer just what to say, but how to say it in a way that invites genuine engagement rather than performative panic, which makes what Webb is planning to do next both scientifically and psychologically significant. Because the next phase of observation is not a continuation of current searches. It is a targeted hunt, using everything the scientific community has learned so far, aimed at specific worlds that now top a ranked list that did not exist 5 years ago. Webb's schedule is finite, its fuel is limited, and its community of users is vast. Getting observation time requires submitting proposals that are reviewed and ranked by panels of scientists who weigh scientific value against feasibility against the cost in precious hours of operation. The competition is intense. The most oversubscribed telescope in history allocates roughly 1 in 5 submitted proposals. The target list that has emerged from this process over the past 2 years reflects a scientific community that is no longer exploring broadly. It is beginning to focus. K218b is already scheduled for additional transit observations specifically designed to push the dimethyl sulfide signal toward or beyond the 3 sigma threshold. Each additional transit stacks more signal onto the existing dataset. The statistical confidence will either grow or, if the signal was noise, begin to dissolve as more data fails to reinforce it. Within the next 2 to 3 years, the field expects to have enough data to know whether this detection is real or a statistical ghost. That timeline is not an estimate. It is a function of how many transit windows are available and how many Webb has observation time to capture. TRAPPIST-1's inner habitable zone planets remain high on the target list. The outer 2 of the 3 potentially habitable worlds have not been fully characterized. Webb is in the process of completing that characterization. Scientists are specifically hunting for water vapor, carbon dioxide signatures, and any indication of atmospheric retention, since the innermost habitable zone world appears to have lost its atmosphere, and the question is whether the others have done the same or held on to something worth examining. A newer set of targets has emerged from the ongoing compilation of Hycean world candidates. K218b was not the only planet flagged as a potential Hycean world when the Madhusudan group published their original model. Several others share similar size, mass, and orbital characteristics. Some are closer to Earth than K218b. Some orbit stars that are more stable, with lower flare activity, which would make them more favorable for atmospheric retention and surface chemistry. Webb has begun preliminary observations on the nearest and most accessible of these candidates. Scientists are also applying a new analytical technique to archival Webb data, revisiting spectra already collected but not previously examined specifically for dimethyl sulfide and related sulfur compounds. This retrospective search is essentially free in terms of telescope time and has already identified a small number of intriguing signals in existing datasets that are now being flagged for follow-up. The 5-year horizon for Webb is not just about confirming or ruling out K218b. It is about building a statistical picture. If dimethyl sulfide is confirmed at K218b, and preliminary signals appear at 1 or 2 other Hycean worlds in the same analysis, the case for biological origin becomes dramatically stronger than any single planet detection could establish alone. A pattern across multiple worlds, in similar chemical environments would be extraordinarily difficult to explain through abiotic chemistry. That pattern-building approach is what separates the current phase of astrobiology from everything that came before. It is no longer about finding one compelling case and arguing over it. It is about accumulating a body of evidence across multiple systems until the weight of it forces a definitive conclusion. The conclusion, when it arrives, will not look like a movie. There will be no spacecraft in orbit, no transmission received, no face-to-face encounter. It will look like a press conference in front of a projected spectrum. A scientist standing at a podium with a graph on a screen, a line in a dataset where a molecule's fingerprint appears with enough statistical certainty to say the word confirmed. That moment is not as far away as it once seemed, and whether humanity is ready for it depends entirely on a question nobody has yet found a clean answer to. Picture the room. It is not a stadium, it is not a broadcast from space. It is a conference room somewhere, NASA Goddard perhaps, or the European Space Agency's facility in the Netherlands, or Cambridge University where the analysis team sits. There is a podium, there are cameras. There is a projected slide showing a spectrum with a marked absorption feature at a specific wavelength. The scientist at the podium is being careful with language, as scientists always are, but the language is no longer uncertain. The signal has cleared 5 sigma. The alternative explanations have been systematically eliminated. The word being used is confirmed. In that room, in that moment, the most consequential scientific announcement in human history will be delivered by a person reading prepared remarks to a room full of journalists who already received the embargo briefing 2 days earlier. The confirmation will not feel, in that moment, commensurate with its meaning. It never does. The announcement of the first exoplanet confirmation felt underwhelming to people who didn't immediately grasp what it represented. The first detection of gravitational waves from colliding black holes, one of the most precise measurements in the history of physics, was announced in a press conference where the audience clapped politely. The scale of what these things mean settles in slowly, over years, as the implications ripple outward through every discipline they touch. Confirmed life on K2-18b will be the same. The press conference will end. The scientists will answer questions. The journalists will file their stories. Most of the world will read a headline, experience a brief moment of awe, and return to everything they were already doing. But something will have permanently changed. The assumption that life is rare, that Earth is a special accident in an empty cosmos, will be gone. Not weakened, not challenged. Gone. Replaced by a demonstrated fact. The universe makes life. In the right conditions, chemistry becomes biology. Biology persists. And 120 light years is close enough to call it local. Every question that follows from that fact will take decades to answer. What is the relationship between the chemistry of K2-18b's life and the chemistry of Earth life? Are the fundamental molecules the same, suggesting a shared ancestry or a shared universal solution? Or are they entirely different, proving that life found 2 completely different routes to the same destination, which would mean the underlying logic of biology is written into physics itself and would work in any solvent, on any world, under any reasonable chemistry? Is there complexity out there, or only microbes? Is intelligence common, or is the silence real in the way the Great Filter predicts? Are we the exception or the rule? Webb will not answer those questions. It will only answer the first one, the one about whether microbial life exists beyond Earth. The rest of the questions belong to the next generation of instruments, missions, and scientific frameworks that do not yet exist. But the journey toward those answers cannot begin until the first one is settled. And for the first time in human history, the instrument capable of settling it is already in position, already operational, already collecting data. 120 light years away, a warm ocean world wraps around its star in a steady, ancient orbit. Its atmosphere carries chemical signals that have been traveling toward us at the speed of light. Webb is catching them now. sorting them by wavelength, measuring the dips and peaks. The answer is already in the data. We are waiting for enough of it to know what it says.